All right, hello class. In this video, we'll be going over inductance. Really, we're just going to look at inductors and RL and LC circuits. So that is circuits that include inductors, resistors, and inductors and capacitors. Just by way of review, if you recall, capacitors store energy in a magnetic field. In an electric field. So if we have a capacitor, then it has energy in it according to the capacitance and the voltage that is stored is in the capacitor. All right, so we have a positive side and a negative side. Inside the capacitor, you have an electric field. So let me see if I can get the exposure up just a little bit. Okay. All right, so an inductor, and I've got an example of an inductor right here. An inductor is really just a coil of wire. All right, so it's a coil of wire. Sometimes, this one's empty, but you can put like a rod in it, which increases the inductance. So kind of like capacitors, you could have them empty, or you could put Teflon inside of them or something else. We can put stuff inside inductors to change their inductance. But that's literally what an inductor is a coil of wire. And depending on how many turns you've got and what the geometry specifications and inside of this is, it has a different inductance. Okay, so just like capacitance is a property of a physical artifact, right? So it depends on the shape, the size, the material composition, and everything. All of that stuff goes into capacitance. The same thing is true for inductors, and inductors. So this is the circuit diagram that we use for capacitors. For inductors, we use a circuit diagram that kind of looks like a coil of wire, like this. And sometimes you'll see it coiled more than others. But the energy that's stored inside of an inductor is equal to 1/2 Li squared, where L is the so-called inductance of the inductor, kind of like capacitance of a capacitor. And I is the current going through the inductor. Okay, so remember, if we have current going through a wire, or in a wire loop, then there's a magnetic field around or through that loop, just like you guys did in lab on Thursday. And inductors store the energy in the magnetic field inside of it. Okay. Now the inductance L has units of henries, H, which and Henry is a volt times the second divided by an amp. Okay, and so that's the units for inductance, and the voltage across an inductor. So I'll grab just a different color so we can put voltage in a different color. So if we have voltage across an inductor, the voltage across an inductor is equal to negative L di dt. Okay, all right, so let's walk through this real quick. So this means that the voltage across an inductor opposes, that's the negative sign, a changing current. Okay, so this right here means that the current if the current is not changing, then there's no voltage across the inductor. All right. The inductance L again is just this Henry value, and then again the negative sign just means that the voltage opposes the changing current. All right, and so this is the way that we can use these as in circuits, okay, because we can apply Kirchhoff's loop law and use this kind of equation. We'll see a couple of examples of that. All right. So in this case, if the voltage is like this, that means that the current is increasing in this direction. Okay. Okay, so the current is increasing in this direction, and the inductor tries to stop it, so it sets up this voltage gradient. Okay, so it opposes this increasing current. All right. If the current is decreasing, then it would flip, right? So it just opposes whatever that change is. If the current is going this way and increasing, so it's opposing the change in the current. Okay. All right. So RLC circuits, RL circuits have resistors and inductors in it, and we're going to take a look at just the basic, one basic type. All right, so let me sketch out an RL circuit. So we will. So this is an RL circuit where I have a resistor here and an inductor here. Now, we're going to give this circuit some initial current, okay? So we're going to give it some initial current and call that I naught, all right? So I naught is the initial current. Okay, and we know that I naught tells us that as it goes through this resistor, delta V for the resistor is equal to I times R. That is, the voltage across this is whatever the current is, all right, times the resistance. That's this delta V. And then the inductor has to have the opposite. We can apply Kirchhoff's loop law to this and say if I go up delta V, I have to go down delta V, right? So if we apply Kirchhoff's loop law or Kirchhoff's voltage law to this circuit right here, we would see that whatever this resistor voltage is, it has to be the same as the inductor, but in the opposite direction. Or we could say it this way, that delta V of the resistor has to equal delta V of the inductor. All right, because those have to be, they have to go up and then down the same amount. All right, and so that's what those are. All right, and we'll just label this one as plus minus delta V of the inductor. Okay. All right, now we can go ahead and substitute in what we know of these two parts. We know that delta V of the resistor is I times R. All right, let's put that in there. And then delta V of the inductor is what we just looked at, which is negative L di dt. All right. We've already seen an equation like this, and we can solve it relatively easily by moving our dt over and grouping our i's over here. So we're going to rearrange it like this. We're going to divide by L, multiply by dt, so that we get negative R over L dt equals, and then on the other side I'm going to divide I over di over I. Right? And then this is solvable simply by integrating both sides. I'm going to integrate from sometime 0 to sometime t, and I'm going to integrate from some initial I to some final I. All right, and so that's what we'll be integrating over. All right, so this left integral right here, the integral of dt is just t. So we get negative r over L times t. And this equals, over here on the right side, this integral is the natural log of I over I naught. All right, and usually we don't see it cast in this way. Instead, what happens is we take e to both sides, right? And so then we can rewrite it as e to the minus r over L t equals I over I naught. Or we can put I naught over here and say I equals I naught e to the negative r over lt, right? So we can rearrange this however we need, but this is the equation that shows you how the current changes in this circuit. A graph of this current looks like this. If we start off at some I naught value here, it's going to decay exponentially like this. All right, and so this is I naught. Okay, we know that I naught is delta V divided by R. So if I know this initial voltage, I can find out what I naught is. So we can analyze the circuit to kind of figure out what the initial condition is and plug that in. All right. Now up here in the exponent, oftentimes this is defined as tau equals L over R. So tau is the time constant. And then we can write the equation as e to the minus t over tau equals I over I naught. All right, so we can use this time constant instead of L over R, and that just depends on how we want to write the equation. All right. This does have units of seconds. Tau has units of seconds. Let's show that real quick. So L is inductance. It has units of Henry, and Henry have units of volts times seconds over amps. And then the units of resistance are ohms. Okay, and in the denominator, an amp times an ohm, which is a current times a resistance, is equal to a voltage. So the volts cancel, and I'm left with seconds. So this gives us units of seconds. All right, there's another, see if I can find another piece of paper. There is another circuit that will come in handy for us to analyze, and that is one where you have a voltage source in it. So let's sketch that out real quick. Where I have some EMF here. And then this is my inductance, this is my resistance. Okay, so I got an inductor and a resistor. And in this case, we would start by charging everything, right? So we would have initially, no energy would be in the inductor, all right? So we would start with no current, and then we would build up current, okay? So we're not going to work through the derivation of this, but just to let you know, the current in this circuit is also a function of time, and it is epsilon over R 1 minus e to the minus t over tau, where tau again is the time constant. Tau is L over R. Okay. So let's look at this equation. Notice where this equation starts, right? When t is 0, e to the 0 is 1. So 1 minus 1 is 0. So the initial current in this case is 0. That means that there's no voltage drop across the resistor because there's no current going through the resistor. However, there is a voltage drop across the inductor, and that's based on the fact that the current is changing. It is increasing. All right. And then at some long time, when as t approaches infinity, e to the minus infinity is 0. So this is just epsilon over r, which is as if the inductor isn't even there. Right, so it's just Ohm's law for this resistor. Okay, so this graph looks like this, where it approaches steady state. The initial slope here is the maximum current change based on the voltage. Okay, so again, it's the same time constant, though. The time constant is what governs how fast this happens. All right, so let's take a look at an example. Got example 14.4. Okay, and so here's the example. In this circuit, which is this one right here, let epsilon equal 2 volts. So that's right here. This is 2 volts. R equals 4 ohms. So R is 4 ohms. L equals 4 Henry. And with S1 closed and S2 opened, which is when this is closed like that, what is the time constant of the circuit? Okay, so the time constant, again, we can just set this equal to L over R. And then we look up, we have 4 Henry and 4 ohms, which gives us 1 second. All right, so the time constant is L over R for these RL circuits. What are the current in the circuit and the magnitude of the induced EMF across the inductor at t equals 0, t equals 2 tau, and as t approaches infinity? Okay, so what happens at t equals 0, which isn't in this part of the prompt, is that at t equals 0, S2 is closed and S1 is opened. Okay? So we get the circuit that we've already analyzed, which is this one right here. Right? We get this circuit when that happens. Okay? So we're going to look at this. B, what are the current in the circuit and the magnitude of the induced EMF across the inductor at these different times? All right, so we need to cast the equation in terms of what's given. All right, so let's just write out the equation like this. Okay, so initially the current is whatever the steady state current was in the circuit before this switch operation happened, right? So remember, we went to steady state at t equals 0. This switch is closed, that switch is open. When that happens, there's current going through the resistor and the inductor based on how long it took for this thing to charge up. Okay? So the initial at steady state, when S1 was closed, is just epsilon over R. This is, let me just go back here. This is what happens here, right? At steady state, you get epsilon over R because this term is 0, and so you get 1 times epsilon over R, right? So as if the inductor isn't there because you have a constant current flowing through the circuit. All right, so approaches steady state. All right, so we can solve for this I naught value, and we get 2 volts over 4 ohms, or 0.5 amps. All right. Now we know all the pieces of this equation. We've got tau is 1 second. I naught is 0.5 amps. We just need to plug in these different these different values. So I of 0, well, if t is 0, then e to the 0 is 1. This is just equal to 0.5 amps. It's the initial current in the circuit. When this happens, S2 is closed, S1 is opened. All right, what are the current in the circuit? Let's say at t equals 2 tau. All right, so that's going to be 2 seconds because tau is 1 second. So then I just need to plug in, I0 e to the minus 2 seconds over 1 second. All right, and then plugging in 0.5 in here, I'm going to get, I punched the numbers into my calculator. I got 0.0677 amps. And then lastly, I as t approaches infinity. Well, as t approaches infinity, e to the minus infinity is 0. So this is going to be 0. All right, so you guys try this one. Hit pause and try this one. Let me just read it to you real quick. After the current in the RL circuit of example 14.4 has reached its final value, the positions of the switches are reversed so that the circuit becomes the one shown in 14.12. So that's this right here. So switch 2 is closed, switch 1 is opened. How long does it take the current to drop to half of its initial value? How long does it take before the energy stored in the inductor is reduced to 1% of its maximum value? All right, you guys hit pause and come back in just a minute. All right. Okay, so let's take a look at this. We've got part A, how long does it take the current to drop to half of its initial value? So in this case, we know that I over I naught is equal to 0.5. And this is equal to e to the minus t over tau. And tau, again, is 1 second. So in order to solve this, I mean, you could use numsolve on your TI-36X Pro, or you can take the natural log of both sides. And you can solve for t this way, which is 0.693 seconds. All right, so that's part A. Part B is how long does it take before the energy stored in the inductor is reduced to 1% of its maximum value. All right, so if we want the energy to be reduced to 1% of its maximum value, we need U over U naught to be 0.01. All right, so that's U is this potential energy, U naught is the starting potential energy, and then U is 1/2 L I squared. And U naught is L I naught squared. Everything in here cancels except for the I's. That's the only thing that doesn't cancel. So I over I naught is the square root of 0.01, and I think that's just 0.1. Because that's 1/100th, and square root of 100 is 10. Okay. So now we can plug this in up here, and we can say 0.1 equals e to the minus t over tau. Using the same process here, we can find out what t is. I have not punched this one into my calculator, so let me do it here. So we'll do negative natural log of 0.1, and I got 2.30 seconds. All right. Okay, we need to cover one more concept. There's actually a couple more in the chapter. One of them is RLC circuits. We're not going to cover that, at least quantitatively, but I do want to cover LC circuits because they're pretty interesting because you can get some oscillations. So an LC circuit is one that has an inductor and a capacitor in it. So if I have a capacitor C and an inductor L, this would be an LC circuit where, let's say, there's initially some charge stored up in the capacitor. Okay, so we've got some Q naught in the capacitor. All right, and all of the energy is initially in the capacitor. That means there's no current moving through the inductor. It's all the energy's here. So what's going to happen is the capacitor is going to want to send energy this way, or send current this way, and the inductor is going to resist that, right? It's going to resist it because it's going to be building up its magnetic field, all right? So at some point, all of the energy will be transferred to the inductor, and so the capacitor will be emptied of its energy, and the inductor will have its energy. And then it will go, and the current will carry through until it charges the capacitor up, where it's backwards from what this is. And then it'll go back and forward and back and forward. So these kinds of circuits allow you to get oscillations. And let's just apply real quick Kirchhoff's voltage law to this. And essentially we're going to do it real simply. We've got delta V of the inductor is going to be equal to delta V of the capacitor. And we can plug in what we know about these, which is this one is negative L di dt. And this one is simply Q over C. All right. Now, I and Q are related, right? Q is the charge that's stored up in the capacitor. I is the movement of that charge. So we can actually relate those two, and we can say that this is actually negative L, and if we let this be, so I is the derivative, the time derivative of charge, dq dt. So if we let that be, if we substitute that in for current, current is the time derivative. So the derivative of a derivative is a second derivative. Okay, so don't freak out about this. Let's just look real quickly at this equation right here. What this equation says is that Q is its own second derivative with some constants thrown in there. Okay, so can you think of a function that is its own second derivative with some constants in there? All right, and if you think trigonometric functions, the cosine function is one such function. The sine function also would serve the same purpose, but we'll just use the cosine function. And the function that satisfies this is the cosine function, where omega is the angular frequency for this oscillation. Okay. All right, so let's figure out what omega is. All right, we're going to just take two derivatives of this. So we'll take one derivative, dq dt. All right, when I take one derivative, the derivative of the cosine function is negative sine. So I'm going to do a negative omega q naught sine omega t plus phi. The omega comes from the fact of the chain rule. I've got to take the derivative of the inside and to get that out. Now I'm going to do this again. I'm going to take another derivative. And then I'll get another omega out. And the derivative of the sine function is the cosine function. So notice that we took two derivatives and we got the cosine function back. We got back what we started with, plus some constants out here. Well, those constants equal the constants up here. So let's figure out what that is. So the second derivative, q double prime, is equal to negative 1 over LC times Q. Well, if I look at these two equations right here, I've got Q is all this stuff. Let me highlight that. This is Q. Down here, that's all this stuff. Okay. I've got a negative sign. That means that this right here and this right here are equal. Those have to be the same, which it is. So the time constant, omega, in this case, or the angular frequency, is equal to the square root of 1 over LC. Okay, so this is going to oscillate with a frequency, an angular frequency of 1 over square root of 1 over LC. Now let me just remind you about this angular frequency. This is in units of radians per second. Now remember, radians aren't really a unit. They're a unitless unit. We just use it to kind of as a placeholder. Okay, so remember there are 2 pi radians in a complete cycle. And so this is related to the frequency, the cyclic frequency based on 2 pi radians being in one cycle. All right, let's take a look at a quick example, and then we'll be done. Okay, an LC circuit. In an LC circuit, the self-inductance, so that's just the inductance, okay, is 2 times 10 to the minus 2 Henry. And the capacitance is 8 times 10 to the minus 6 farads. At t equals 0, all the energy is stored in the capacitor, which has a charge, which has charge 1.2 times 10 to the minus 5 coulombs. What is the angular frequency of the oscillations in the circuit? Okay, so for part A, the angular frequency is omega. So that's 1 over root LC. Which is 1 over 2 times 10 to the minus 2 Henry and 8e minus 6 farads. And I did this, I got 2,500. And I'll go ahead and just, you can write per second, but I'm going to put radians per second just to remind you this is an angular frequency. All right, part B, what is the maximum current flowing through the circuit? All right, so for part B, we need I. Well, I is just the time derivative of Q. All right, so if I take the derivative of this, we just did it. It's negative omega Q naught sine omega t, where we're not including the phi, which is the phase angle, because at t equals 0, all of the energy is stored in the capacitor. So we don't need that phase angle. We can just drop it 0. All right, so when is this at a maximum? This is at a maximum when the sine function is 1 or negative 1. Right? So that's all we need. I max is going to be omega Q naught. So I've already got omega. And then Q naught is 1.2 times 10 to the minus 5 coulombs. I got 3 times 10 to the minus 2 amps, because a coulomb per second is an amp. And remember, radians aren't really units. They're just a placeholder, just to let us know we're talking about angular frequency. All right, you guys try parts C and D. So part C, how long does it take the capacitor to become completely discharged? And D, find an equation that represents Q of T. All right, so for part C, I think it might be helpful to just sketch out a graph of what this looks like. So if we were to graph the charge on the capacitor, Q, we'll just call it Q, as a function of time, it's going to look like this, right? It's going to be a cosine function. Cosine functions look like this. And from here to here is one complete cycle. This is 2 pi radians. Right? And what we want to know is how long it takes the capacitor to become completely discharged. Well, it's discharged here, it's discharged there, and there. We're going to look for this first one, right? This is 1/4 of a complete cycle. In other words, the argument of the trigonometric function is 1/4 of 2 pi. 2 pi over 4. This has to equal omega times t, because that is when this thing is 0. So when I look at this, I can just solve that because I know omega is 2,500 seconds. So t is 6.28 times 10 to the minus 4 seconds. All right, so that's t. Part D is find an equation that represents Q of t. We can do that. I could put it up here. Let me put it on at the top. So for part D, Q is equal to Q naught cosine omega t plus phi. Let's go ahead and put it all in there. All right. Now we know at t equals 0, all of the energy is stored in the capacitor. So that means that phi has to be 0, because when the cosine function is 0, this is at a maximum. So phi is 0, and omega, we already got omega, is 2,500 radians per second, and we know what Q naught is. All we need to do is plug everything in. So we're going to plug in 1.2 times 10 to the minus 5 coulombs. That's Q naught. And then we've got the cosine of 2500 per second times t. And there's our equation for the charge on the capacitor. All right, you've got some homework questions. Your homework questions are just some RL and LC circuits. Let me know if you have any questions. I'll be happy to answer.